A2. So this is another titration problem. And so now for this one again, right, like I'm asking to do the sketch at the beginning. And so this, right, is a problem where we have a weak acid. We're titrating it, right? So it starts off at 25 milliliters. It's 0.5 molar solution, right? So we already know the concentration at the beginning. We're going to do that titration with 1.00 molar NaOH. We have the Ka value, right? So that's 8.4 times 10 to the negative 4. And so now we're going to do a whole bunch of titration related problems related to this. So the first thing, right, is asking to sketch the titration curve, right? And then just simply do a qualitative one, right? So again, I always recommend doing this no matter what the titration is, even if you're asked to do it or not asked to do it, because it makes it a lot easier to figure out what you're going to be doing in each one of those scenarios. So what I have right here, right on the y-axis is the pH. Here at the bottom, I have the amount of NaOH added, right? The volume of that. And so, you know, you're always going to start off at a low pH, and it's going to jump up briefly, and then it's just going to kind of plateau, and it's going to go up, and then you're going to have a huge rise, and then it's just going to keep on going up then from that point forward. So if we're looking at it, right, the equivalence point is going to be the halfway point of that huge rise that you have right there, right? So this is going to be the equivalence point right here. And so what we know about the equivalence point is that the number of moles of NaOH is going to be equal to the number of moles of HA. And that then also means, right, that A minus, right, that concentration is dominant. And that's going to then determine what the pH is in that scenario. The next thing is, right, the point where the pH is equal to the pKa. That's going to be the halfway point between the starting and the end, right? And that right there is going to be the point where the pH is equal to the pKa. And that has to do with the fact, right, we can just think about it from the Henderson-Hasselbalch equation, where at the halfway point, right, you should have converted half the amount of moles of the acid into the conjugate base. And so that means then that the concentration for both of those should be equivalent. And so if you're looking at the ratio, that ratio should be equal to 1. If we use the Henderson-Hasselbalch equation, right, which is pH is equal to pKa plus the log of that ratio, the log of 1 is equal to 0. And so then that from there, right, pH is equal to pKa, right? And so that's always going to be the case for a titration, is that the halfway point is when the pKa and the pH are equal to each other. And that can always be a problem. I think there might even be a problem that I have in the GPS packet, right, is trying to figure out what the pKa is of, you know, based off of the titration, right, where you can then easily figure out where within that, you know, system you actually are. Right. And so that's, again, like ways that people are able to figure out, you know, the Kas for things, right, is if you can, you know, measure the pH or figure out like how many, you know, what the pH of the equivalence point is, right, you can easily figure all those things out. So that's, you know, pretty exciting stuff. So yeah, so that's, you know, part 2 right there. So, right, so then part 3, pH depends on HA, right? So the pH of the HA only happens right here, right? So HA is the dominant species right here. And so that right there, right, you're going to have to then use the weak acid equilibrium approach. And then up here, right, this is where then the concentration of OH minus, right, is dominant. And so it doesn't even matter what's going on with the weak acid base, because it's been completely, like, the acid's been completely neutralized, and any OH minus that's being added, right, is just going to be, you know, even though there's an equilibrium still that exists between the HA and the A minus, it's going to completely overwhelm, you know, any of those species in terms of figuring out what the actual pH is, because the OH minus is just going to be completely dominant. Right, but those are the different points on a plot, right? And the other thing, right, to think about is that basically in this region right here, right, is where you have, you know, you can consider this to be the buffer region. And so you can use the Henderson-Hasselbalch equation to make your life a lot easier. Cool, right? So that's A, right? That's how you sketch those out. So B, calculate the pH after 4.25 milliliters of 1 molar NaOH is added to 25 milliliters of 0.500 molar HA, right? So what we have right here, starting off, right, is we're doing the titration. And so now we have to figure out how many moles of, you know, HA has been neutralized by the NaOH addition. So the first thing that we want to do is we want to calculate how many moles of each one we have there, right? Because what the reaction is that we're going to be looking at is going to be the reaction of the HA plus the O minus to form H2O plus A minus, right? That's going to be a reaction that's going to go to completion. I know in the previous packet, right, we had worked through some of those things right there. You could see that the equilibrium was incredibly dominant towards the, you know, pushing everything towards the product side when you have a strong like OH minus present or H3O plus present, because those are just so strong that the equilibrium is so in favor of it going towards the product side in those cases that you don't have to think about that back reaction even like happening, right? It's going to be completely negligible. So we can just, for simplicity's sake, consider it to be a reaction that goes to completion at this point, and there is no equilibrium that exists yet, right? Because we can do the equilibrium part in a moment where we figure all of that out. So what we're going to do now, right, is we're going to set up an ice table right here. And so the first things we need to do is we need to figure out how many moles of HA we have. So we have moles of HA. So that's going to then be equal to the concentration of HA, right? So that's 0.500 moles per liter, right? And that's going to then be divided by be multiplied by the volume that we have, right? So that's 25.0 milliliters. And so we have to convert the milliliters into liters. And so that's going to be 1 liter over 1,000 milliliters, right? So milliliters cancels, liters cancels. We end up only with moles. So the moles of HA that we're starting off with is 0.5 times 25 divided by 1,000 is 0.0125 moles, right? So that's our starting off for HA. So 0.0125 moles in this case. And then the moles of NaOH that we're using is 1.00 moles per liter times 4.25 milliliters times 1 liter over 1,000 milliliters is equal to, right, milliliters cancels, liters cancels. We end up only with moles. We have 1 times 4.25 divided by 1,000 gives us 0.00425 moles, right? So that's how much OH minus we have, right? Because we can consider the dissolution of NaOH to just completely go and form, you know, sodium and hydroxide. So we have 0.00425 moles, right? And so then in this case, right, there's no, we don't worry about the water, right? And so since we're at the beginning part 2 of this reaction, right, there's going to be 0 moles of A minus that's happening, right? We're at the beginning of this titration. And so in this case, am I still streaming? Yes. Okay, good. Right, the change, right, looking at that, the limiting reagent in this case is going to be the OH minus. And so we're going to consume all of that. So that's going to be minus 0.00425 moles. In this case, we're going to consume that much of the HA as well. So that's also going to lose 0.00425 moles. And we're going to gain 0.00425 moles of A minus. So at the end, right, we're going to have 0.00425 moles of A minus, 0 moles of OH minus, right, for simplicity's sake right now. And then we're going to have 0.0125 minus 0.00425 comes out to being 0.01005 moles of HA, right? So we're looking at this right here, right? So we've neutralized, you know, about, what? That doesn't seem right. Yeah, that's not right. I typed in the wrong number. 0.0125 minus 0.00425, not 0.00245, right? So that comes out to being, right? Again, always pay attention to you know, don't automatically trust what you have. So that's going to be 0.00825 moles, right? So we've used up about, you know, roughly a third of the HA, right, with that first addition of OH minus. And so what's, you know, what that should tell us now is that we're going to be in this buffer region right here, right? So we're going to be somewhere over here, right? Because we're not at the point yet where the number of moles of A minus is going to be equal to the number of moles of HA. But because we're in the buffer region, we can use the Henderson-Hasselbalch equation, right, to figure out what the pH is, right? We don't have to go through doing a whole, weak acid equilibrium thing and making ourselves all confused and stuff, right? We can just use the Henderson-Hasselbalch equation at this point. And so that equation, right, is pH is equal to the pKa minus, right? Oh, plus the log, yeah. Right, plus the log of the concentration of the acid over, or sorry, the base over the acid in this scenario. Right, so we have that right there. Now, the thing that we can do too, right, we don't have to, technically, right, it's the concentrations, but because they're in the same solution, the volumes are exactly the same, right? Concentration is just simply moles over liters. The liters are going to cancel out, and so all we have to do is figure out what the ratio of the moles is in this scenario, right? And we can plug all of that information in right there. And so the next thing that we have to also do, right, is that we have to make sure that we calculate the pKa, right? And so the pKa, I'm just going to do that down here real quick, right? The pKa is equal to the negative log of the Ka. And so that in this case for HA, that's negative log of 8.40 times 10 to negative 4. So that comes out to being negative log of 8.4 times 10 to the negative 4, 3.08, right? So that's the pKa in this case. So we can take that, right? So we can plug that in. So 3.08 plus the log of, right? So the number of moles of A minus that we have right now is 0.00425 divided by the number of moles of HA that we have at this point within the titration is 0.00825. So we take all of that, plug all of that into our calculator. So we have 3.08 plus the log of 0.00425 divided by 0.00825. That gives us a pH of 2.79, right? 2.80, right? Same thing. Again, right? Probably a sig fig thing somewhere, right? But that's, how you get the pH there, right? And again, right? Like identifying where within the titration you are and what equation is the most appropriate thing to do, right? Is a very important part of doing these titrations. So identifying, right, that because we've added a significant amount of base already to it, that we converted, a third of the acid into the conjugate base of it, right, tells us that we should be in the buffer region. And if we're in the buffer region, right, we can use the Henderson-Hasselbalch equation because it'll make our lives a lot easier. So yeah. Part C, calculate the pH after 12.5 milliliters of 1 molar NaOH is added to 25 milliliters of 0.5 molar HA, right? So now what we're going to do is calculate this value, right? So what we're doing in this scenario, again, we can just write out what the equation is or what the reaction is, right? So we have HA plus OH minus, let me give myself some more space here, plus OH minus, going to go to completion to form H2O plus A minus in this case, right? So we have our little ice table here. So again, what we can do, right, is we can calculate how many moles that we're starting off with, right? So we have moles wise, we have moles of NaOH that we have right now is going to be equal to 12.5 milliliters times 1.00 molarity, right? Which is moles over liters times 1 liter over 1,000 milliliters, which comes out to being 12.5 times 1 divided by 1,000 comes out to being, right, because the liters cancels, milliliters cancel, we end up only with moles, which is 0.0125 moles in that case, right? So that's how much NaOH we have. So we have 0.0125 moles in this case. And we can go back, right, look at part B again, right? So we started off with 0.0125 moles as well, 0.0125 moles in this case, right? So we have those. And so then the next thing we can do, right, is we can just simply, right, and we have 0 of A minus, right? We don't care about the water. Right, look at it. They're equivalent to each other, so they're both going to get completely consumed, right? So there's no limiting reagent, 0.0125 moles is how much we're going to lose of the HA. We're going to lose 0.0125 moles of the OH minus, and we're going to gain 0.0125 moles of A minus, and so we'll have 0 of HA, 0 of O minus, and then 0.0125 moles of A minus. Now, the important thing now to figure out, right, is that we're at the equivalence point, right? And so at the equivalence point, the HA has been completely consumed by the OH minus. And so that means now that the dominant species in the solution is the A minus, right? The conjugate base that we have. And so now the dominant reaction that's going on, post, neutralization is the reaction where we have A minus aqueous plus H2O liquid is an equilibrium to form HA aqueous plus OH minus aqueous, right? So that's the dominant reaction that's happening now in the solution. So if we set up our ice table in this case, right, we need to first calculate what the concentration of A minus is. So the concentration of A minus, right, that's going to be equal to the number of moles of A minus, which is 0.0125 moles divided by the volume. Now the volume, right, is going to be equal to 12.5 milliliters plus 25 milliliters, right? So the volume is equal to, what is that? 27.5. I can do, or 37.5. I can do that without doing it in my head. 37.5 milliliters, right? Which is the same as 0.0375 liters. So I plug that in, 0.0375 liters in this case. So the concentration of A minus is equal to 0.0125 divided by 0.0375 is 0.333 molarity in this case right here, right? So we have that right there. Right, so we have that. So that's going to be, we plug that into our ice table. So we have 0.333 molarity, right? Water, who cares about that, right? And then we're going to, because we're just treating this standard, weak base dissociation reaction, right? We're going to say that we're going to have 0 of HA initially and 0 of OH minus initially. And so now the change is going to be minus X and then plus X and plus X. And so what we'll have at the end is 0.333 minus X, and then X of HA and X of OH minus. So we have that right there. So now we can set up our equilibrium expression. So that's going to be Kb, right? Because this is the base dissociation reaction that we're looking at right here, right? Because it's going to be taking the base, reacting with water to form the conjugate acid and OH minus. And so now that equilibrium expression has the concentration of HA up top times the concentration of OH minus up top divided by the concentration of A minus. And so if we plug in our values that we have, right, we have X times X, which we can just simply refer to as X squared, divided by 0.333 minus X. I made that line very long, right? And so that's going to be equal to Kb. We don't directly know what Kb is right now, but we do know what the Ka is. And so we can easily figure that out, right? Because that's going to be Kw is, divided by Ka. And so Kw is 1 times 10 to the negative 14. Divided by the Ka, which is 8.40 times 10 to the negative 4. 8.40 times 10 to the negative 4. Right, so we have that. Plug that into our calculator. What we have is 1 times 10 to the negative 14 divided by 8.4 times 10 to the negative 4 gives us a Kb value of 1.19 times 10 to the negative 11. Excuse me, in that case. So what we can do now is we can then now solve for X. And so to do that, right, we can have X squared is equal to, right, because we can use the 5% approximation right now. We can just assume that X is going to be completely negligible in terms of changing the concentration of A minus. Right, so we can just cross that through. Right, and so what we get is x squared is equal to 1.19 times 10 to the negative 11 times 0.333 is 3.96 times 10 to the negative 12. So if we take the square root of that, what we get is 1.99 times 10 to the negative 6, right? And that's going to be equal to x. And that's going to be equal to the concentration of OH minus. And so now, right, if we're trying to calculate the pH, we can just simply use the derived equation that we've done in the past, where we have the pH is equal to 14 plus the log of the concentration of OH minus. So we take that, right, 14 plus the log of, what is that, 1.99 times 10 to the negative 6. What we get is the pH is equal to 14 plus the log of 1.99 times 10 to the negative 6. 8.30, right? Which is what I have on the key. Right? And that's how you approach that part of the problem. Right there, right where we're at the equivalence point. So again, right, identifying where you are within titration, very, very important. Cool. Oh no, is it doing this to me now? Oh, digga. I'll be back. I'm gonna go grab another keyboard. Alrighty. There we go. Right. So yeah. So that's that problem. Right. Yeah. That's A2. That's how you solve those things. FYI, anybody who's like actually watching, if there's a specific problem that you had voted on that you want me to work on, like let me know, just because it's already 10:30. And I have a meeting at, I think, 11:30. Let me double check that I know I have to go to. No, at 11 even. So if there's a specific problem that you are here to watch me work on, let me know. I'm just going through all the things that people had voted on. But if you're like actually viewing, just let me know, what you would actually want me to work on right now. All right, cool.